A problem you may recall from Calculus 2 was utilizing polar coordinates to be able to find the area inside of a sort of a geometric shape in polars. This one a cardioid, defined as r equals 1 minus sine theta. Alright, you may remember from Calculus 2, cardioid, heart-shaped, okay, like cardiac. Okay, so just some stuff from Calc 2. And if you were to go into your calculator, put the mode into polar coordinates, you'd probably get a graph that looks something like this. Okay, so it has this sort of shape, and then it comes down. Alright, it's probably not the best construction that I could give, but that's what I have. Now I want you to notice that the radius is not defined as a constant this time. Okay, so radius here is different than the radius here, is different than the radius here, is different than the radius here. So the radii are going to change completely based on what r is. The other thing that we have to be concerned about is what theta would be. All right, so here's how we're going to evaluate this. Okay, we're going to evaluate and say that this is going to be the double integral from 0 to 1 minus sine theta. All right, if you'll notice, the radius r, the smallest it could possibly be is the distance from the origin up to that dimple. So that's 0 to 1 minus sine theta, unlike the other problems where they were all circles, meaning that r was a constant. And then theta, well, we didn't really say anything about theta. It's not bound in quadrant 1, quadrant 2, above the x-axis, etc. So this is going to be from 0 to 2 pi. Well, usually we would just say dx dy or dy dx. Instead, we're going to now have r dr d theta. All right. Generally, when we start out and we just want to find an area, we usually just have like an integral of dA, or in this case a double integral of dA. So we're just going to use r dr d theta. All right. Now we can't break this up into two separate integrals like we have in the previous problems. All right, so we're going to have to do it one at a time. The reason we can't break it up is because one of the bounds is indeed a variable bound. So integral 0 to 2 pi, excuse me. Integral of r dr, that's just going to be r squared over 2 from 0 to 1 minus sine theta. We still have that d theta. All right. We're going to substitute 1 minus sine. We're going to substitute 0. So this is now 0 to 2 pi. If we substitute 1 minus sine theta, I'm also going to factor out the 1/2 just out of convenience. Okay, so this 1/2, just going to pull it out front. So we're now going to get 1 minus sine theta square minus 0 square d theta. All right. Or, in other words, that just becomes 1/2 of the integral from 0 to 2 pi of 1 minus sine theta quantity square d theta. All right. Now, this we're going to have to go back to Calc 2 to be able to evaluate. I want you to notice that if there was a cosine on the outside, all right, that would be really nice, but there is not a cosine. So unfortunately, we can't utilize the idea of a u substitution. All right, so what we're going to have to do is we're going to have to revert back to some techniques of integration. Let's FOIL this out. By FOILing, we have 1/2 integral from 0 to 2 pi. We're going to FOIL that out, so we're going to get 1 minus 2 sine theta, so you just double the product of the two terms, plus sine square theta, d theta. All right. Two of the terms are extremely easy to evaluate. The first two are basic antiderivatives, which we could evaluate. Sine square is not basic. To evaluate sine square, okay, what you probably have to remember is that there is a power reducing formula. Right? So this is going to be a technique that we might have to utilize a few times. Okay, so I'm just going to abbreviate that, power reducing formula. And you may remember the power reducing formula is 1/2 minus 1/2 cos of 2 theta. Okay, that means sine square of theta is always equal to 1/2 minus 1/2 cos of 2 theta. Alright, so try to get used to utilizing these sort of trig func formulas or these trig reduction formulas. You probably remember seeing it from Calculus 2, but if not, there is a reminder. Alright, so once again, I'm going to rewrite our expression. I'm going to rewrite it a couple times. 1/2 integral 0 to 2 pi. We still have the 1. We still have the 2 sine of theta. Instead of sine square of theta, we're going to write that as 1/2 minus 1/2 cos of 2 theta. All right? And then we still have our d theta. Clearly, we can combine like terms. We have a 1 and we have a 1/2. So we're just going to add those together. So one last simplification before we get to it. 0 to 2 pi. So we're going to have 1 plus 1/2, which is going to be 3/2. So let me go back. So we're going to have 3/2 minus 2 sines of theta, and then minus 1/2 cos 2 theta. And then we still have our d theta. All right. Now we're set for integration. All right. All three of these are basic antiderivatives. The last one you'd need a u substitution, or just to remember that if you have an embedded trig function or an embedded expression that is not a square or a square root, it's just a linear term, instead of multiplying by the reverse of the chain rule, you would divide by the coefficient. All right. So here's what we end up with: 1/2 antiderivative of 3/2 with respect to theta. 3/2 theta. Antiderivative of 2 sine is a positive 2 cos theta. Okay, so remember, antiderivative of sine is negative cos theta. So we have a negative and a negative, which is going to turn it into a positive. All right. Antiderivative of cos is going to be sine. Now we have a 2 theta in there, so this is going to turn into minus 1/2 times another 1/2, okay, and that's a result of the chain rule, the reverse of the chain rule. Usually with differentiation we add, or multiply, excuse me. Now we're going to divide. We have sine of 2 theta, and it's going to range from 0 to 2 pi. All right, so now we get to evaluate and simplify. Scroll down just a little bit. This now becomes 3/4 theta plus cos theta. All right, so we have a 1/2 times a 2, so we'll distribute, we distribute, we distribute. Minus a half of a half of a half is an 1/8 sine of 2 theta from 0 to 2 pi. All right. We're going to substitute 2 pi. We're going to substitute 0. Now, because it's trigonometric in some of the aspects, we can't just expect 0 to wipe out. Okay, it's going to contribute to the sum. So by substituting 2 pi, we get 3/4 2 pi plus cos of 2 pi minus 1/8 sine 2 times 2 pi. All right, so that's 2. Now from that, we're going to subtract substitution of 0. So 3/4 times 0 minus cos of 0 minus 1/8 sine of 2 times 0. All right, now it's trig time. Good news is, a few of these are going to go away inherently. All right, so 3/4 times 0, that's just 0. the negative 1/8 sine of 2 times 0, that just becomes 1/8 sine of 0, negative, and that goes away because sine of 0 is 0, so that term just goes away. Another thing that's going to go away is the minus 1/8 sine of 2 times 2 pi. All right? Remember that 4 pi is 2 complete revolutions, which means it's coterminal with 0 radians. All right? So this is going to go away as well. All right? So the good news is now we're left with only a few things, okay, or a few items. So we're going to have 3/4 times 2, 3/2 pi. We have cos of 2 pi, and then we have minus cos of 0. All right. We know that cosine of 2 pi is actually coterminal with cos of 0. Or we could just use our calculators. So we get 3/2 pi plus 1. Cos of 0 is 1. So this ultimately just turns into 3/2 pi. All right. So before you go on to the next problem, take a look back at this one. Okay, make sure that you're okay being able to set this sort of thing up. And then what I would encourage you to do is to maybe set up the next example, and then as well as the next example after that, just to see how well you can go with the polar coordinate stuff. And then try to evaluate both of those by utilizing what we've done in the first 3 of these examples.